In this assignment, we will explore computation of viewsheds and solar energy potential. I have already created a new map set, assignment 6, and switched to it. I have downloaded viewshed points into my directory where I store my reports, and I have created a subdirectory for homework 6. And then I have changed to that directory using the cd command. So I'm now ready to do the viewshed analysis. So in the first step, we will compute the viewshed, the areas that are visible from a 32-story tower located downtown. So we have coordinates for that location and elevation above ground set to 165 meters. So we set the region to the digital elevation model that we will be using. It's a 30-meter resolution. Then we will import the points that we will be using as viewing points. And then I will be computing the viewshed from this building and limiting the distance of that viewshed to 10 kilometers, 10,000 meters here. And now you think I'm getting this very strange image. So what do I need to do? I need to zoom to computational region. So now I have, this is the location of that building, and this is the area that I can see from the top of that building. So let's create some maps, let's add some additional layers for context so that the map is not as abstract, so that we know where we actually are. So I will erase what I have there, and then I will use the command d.his to mesh the elevation shade, the shaded topography with the viewshed. So that will show me how the topography looks like in that area. And I may want to do it, make it a little bit brighter under this optional. Let's put there 30%. Okay. And then I will add also streets. So this shows me really that the building is downtown Raleigh. And let's add the viewing points that we will be using, and I will increase the size so that you can see it a little bit better. So here is our viewing point. Let's add the bar scale. And the legend, because you can see it's almost all of it is the same color, but there is some change in colors here. And what this map represents, it represents not only what we actually see, but what kind of angle, under what kind of angle we see it. So let's just put the legend there, and then we can talk about the angle. And I will put it here. So when we are looking straight ahead, then that's around 90 degrees. When we are looking down, that would be like exactly down would be 0. So you can see that very close to the building to see the ground, we are actually looking at very low angle. And then most of the area we see just looking straight ahead. So now we can save this image for our report. And we want to know, like, what do we actually see in terms of land use. Is it mostly developed area? Is it forested? Is it agriculture? So we can use map algebra to extract land use categories for this viewing area, for this view shed. So if this viewshed layer is not null, then we will, if it has some value in it, then we will assign all those grid cells land class. If it is null, then we will carry over that null value. Then we will assign the output map the same colors as we have in the land use map. And to create a legend, we will carry over to this file also the labels, the category labels from the land use map. That's the command r.category. And then we will run the report so that we can see what kind of categories we have there. So there are 7 categories, and we have the developed area is the highest coverage. So most of what we see is the developed landscape, but there is also 37% of that cover is forest. So even as it is developed, a lot of that is under the trees and is classified as forest. So now let's create an output map for our report. So I will erase everything, including the legend, and display the land use in our viewshed, streets for reference, and then the legend. And you can just keep it here, make it maybe smaller. And we can save this map for the report. And we can compare this viewshed with a viewshed from a different location. So this location is relatively low, it's downtown, but the building or the viewing point is very high above the ground. Now we will compare it with a viewing point which is at a higher elevation, but it is the above ground height is much smaller. So the observer elevation is only 25 meters compared to 165 meters. But if you query the digital elevation model at these 2 locations, you will see that it is that this point is at higher elevation. And again, we will display this map, create a map for our report. So you can see that although this is the first location, this is the second location, and in spite of the fact that the location is at higher elevation, because the building is much lower, just 4 stories compared to 32 stories, our viewshed is actually significantly smaller. And then you can run r.report to find out how big it is, and you will do yourself again, extraction of land use categories and create a land use category map for this viewshed and compare the composition of that viewshed with the composition, land use composition viewshed for the downtown point. So we can just save this one for the report, and you will do the rest, the similar analysis of land use as we did for the downtown location, for this location by yourself, and make sure to answer and comment on your comparison. So let's now move on to solar radiation analysis. So we will switch our region to that rural area, and we will be now working at 1 meter resolution. And what we will do, we will use map algebra to add a building to that little watershed that we worked with in some of our last assignments. So let's switch the region. Then we will add that building using this map algebra operation, and the rectangular raster polygon that I have here, it's called facility. And you can just display it to see what it is. And here I am using it in that map algebra operation to add that building to the topography. And I will now change the color of the output. And you can see this is my study area here. So what I do, I need to zoom into computational region. So here is my digital elevation model with this added building. And let's just erase it. And let's just put it there again. And just so that you see how it actually looks like, we can switch to 3D view. Mm-hmm. And, oh, no. Let's just zoom out a little bit so that you can see how that topography looks like. So we will have this topography with this massive big building on it with a flat roof. So let's go back to 2D view. And let's compute slope and aspect that we will need to compute the solar inclination angle and solar irradiation. So that's our aspect, and this is our slope map, and you can see that the roof is completely flat. Now, the command that computes solar radiation requires us to define a day for which we are computing the day and time for which we are computing the solar inclination angle and irradiance and other parameters. So to find out for a given date what would be the name and also other parameters related to the position of sun, let's just use this sun mask command. And the sun mask command actually computes shadows, but we are running it here only with the outputs that will tell us what is the day number for our date. And our date would be December 22nd at 2:25 p.m. EST. So let's just run it. And what you have here that for this date, day number is 356. The latitude and longitude that is being used is from this region, and we also get the solar position. And you may recall from the lecture that you have the sun azimuth and sun altitude, and then it will also give you sunrise and sunset times. So now what we can do, we can compute that incidence angle. Spatial distribution of the angle between the normal to topography and the solar beam. For this particular day, which is actually winter solstice. So what is the range? And the range of values is between 3 to 87 degrees, 82. And then we also have here all those parameters that are related to the solar, to the sun position for that day, and for all the other additional parameters that are used in this module. So let's just change the colors here, because we have almost all of it is the same color, so that we can highlight the spatial variability of the solar inclination. And the reason why we have it is that we have both the flat roof and also almost completely vertical walls. So let's just do a histogram equalized table. So here you can see much better how the inclination angle is related to the topography. And let's just add the legend. Can move it here. And let's just save this map for our report. And let me just remove these other ones. So you can see that this white area is the area actually of cast shadow. So let's now compare cast shadows for the same day, but different times. So we have computed the cast shadow and the distribution of inclination angle for the 2 p.m. time, so that's 14.4 hour, and we can extract it now using map algebra from our map, and then we can compute the cast shadow for the morning of that day at 7.5 p.m., 7:30 p.m., and then we will compare how big these shadows are. And these are good examples of within this entire assignment, you can see good examples how the null values are used in map algebra. So let's extract the shadow, and we will assign it gray color. Let's erase it. This is our DEM. This is our cast shadow. And let me remove this. And let's just save this map. Now we can compute the inclination angle for the morning hour. And now the cast shadows are these orange colors, and that's actually our DEM under it. So when we switch it off, the white color is where we have a shadow. So now let's extract that shadow. Let's color it gray. Okay, let me just do it again. Mhm. Now I got the color. And let's just show it along with the digital elevation model. Okay. And we can save that map. Now you are supposed to answer a question: how does the cast shadow area change? So you can compare it visually and compare and comment on the visual comparison, but you can use r.report to actually provide a quantitative assessment. So you would just run r.report on the first and second shadow map for the non-null areas. Will show you where the cast shadows are and how big that area is. Now let's move on. So we computed the solar inclination angle, and we extracted cast shadows so that we can see where we have no solar rays reaching and where we wouldn't have any solar irradiance at that moment. So now we can move on and compute the solar irradiation for entire day. So the inclination angle we have computed just for that particular time, for that particular instant. Now we will be aggregating, integrating essentially the values over the entire day. That means that we are computing it for every 30 minutes. That's the default compute time step, and aggregating those values to compute a total solar irradiation for the entire day and its spatial pattern over this area. And we are computing global irradiation, and that means that we are computing both the direct and the diffuse and the reflected irradiation. And you can output the other ones as well if you would like to see how the direct, like beam irradiation, compares to diffuse, for example. So now the computation runs a little bit longer because we are computing the entire day. Okay, so this is the number of hours and spatial distribution of hours for how long each grid cell is illuminated by sun. And this is the actual irradiation, and we will change the color table and create appropriate map. So here it is with changed color table. So I switched off the the time. So this is the global irradiation for the winter solstice. Now let's compute it for summer solstice. It takes slightly longer. We have more hours of sun. You can see longer hours, and we will add the legends in a minute. We will change the color table. Again, you can see very different spatial distribution of solar radiation. Now let's just erase everything. So this is our global irradiation for the winter solstice. Here is the legend. So here we have the values. Okay. And let's just save it for our report. Now let's do the same for summer solstice. And we will need a new legend. And for this legend, I am only extracting the values, the top values, essentially those values that we have there. And I am doing this just to show you how different those values are, that during the winter, we don't have a single grid cell that would reach the amount of solar energy that is comparable to the amount of solar irradiation that we get for almost every cell during the summer. So big difference between the solar irradiation during the winter solstice and summer solstice. And of course, those 2 days are extremes. So during the year, we will have the values somewhere in between. So your task here is to look at these maps, display also the hours. So let's just save this one. And I will keep the other legend there as well. And let's now display also the time. And so this would be spatial distribution of the number of hours that each grid cell is illuminated by sun and receives some solar irradiation. So this would be for winter. And now let's just do it for summer. And I have a new legend, and I'm keeping the other one there just to compare. You should remove it for your report. And you can see that these are much longer times. So let's just remove these other legends. Oops. And I will zoom back to computational region. And let's save this map for our report. So please discuss these differences in your report. And what you can also do, you may remember that at the very beginning, I have displayed the digital elevation model, and I think that's this one. So what you can do, you need to switch off all these other layers. You can now switch to 3D view and use the time and or the solar radiation as a color on your 3D model. So let me just try doing that. So let's go to 3D view. So here is our building. I need to make sure to change the fine resolution to full resolution. So let's put it to 1. So now I have the full resolution. The building is better represented. And then here I am showing it with the elevation color, so I can display it with, let's see, the solar irradiation for the uh, summer solstice. So you can now see what I have on the top of the building, what kind of values we have on the side of the buildings, and how is the solar radiation dependent on the topography on the southern slopes and the northern facing slopes. And what I would like you to compare, for example, where is the maximum and minimum solar irradiation, for example, on the building during the winter, and where it is during the summer. So let's look at the summer distribution. Okay, so you can see that there is a big difference in what is on the top of the building and what is on the side of the building, and also the distribution is quite different because we have the sun much higher in the sky compared to the winter. And you can of course display some of these other parameters that we have computed, such as the number of hours. So again, like most of the area gets the same number of hours, but there are certain locations like here in the shadow that have lower number of hours. Okay. And then the last task is optional. So you just change the region and calculate the, direct solar irradiation and insolation for a larger region. And then you can comment on how this, what is the pattern in terms of northern and southern facing slopes.